We're going to be talking about exponential functions, specifically some different ways that we can apply exponential functions or their equations to some real-life scenarios here. One of the most important things being a financial application, some calculating interest for investment purposes. If you are familiar with using this formula, then the chances of you getting ripped off by a scam are less likely, and your chances of using it in a positive way to invest and increase your financial gains in productive ways will be a lot more possible. We have two different versions of a compound interest. We have this formula. That's if we are evaluating our interest multiple times per year. We could do that a variety of different ways per year. We'll talk about that in a sec. No financial institution that I know of is willing to compound your interest or evaluate your interest continuously, but we're still going to practice doing it. This is actually more of a formula that's used for other applications such as science or statistics. We'll talk about that in a sec as well. All right, let's go back up to this first one. So lots of different variables involved in this formula. So let's break those down. The A would be the amount earned, or the answer after you evaluate all of this. That would be the total amount in your bank account. The P is going to be our initial amount that we start with. It's called the principal. R is going to be represented by the interest rate, which is usually given to us as a percentage. But we're going to use it as a decimal in our equation. N is going to be the number of times that your interest is compounded or simply evaluated per year. And so that could happen in multiple different ways. We could just do it once per year or yearly. So in that case, our N would be 1. We could do it semi or biannually or yearly. And that would mean that N happens twice per year. We could happen quarterly, which happens 4 times per year. Monthly would happen 12 times per year, and weekly would happen 52 times per year. Very rarely do we ever use weekly. More often we're doing it monthly or quarterly or biannually or yearly. So in this first example, we're going to start with $5,000. We're going to put that into our bank account, and it's going to invest or calculate our interest at 4%, so 4% of our $5,000 every year. We're doing it annually, so once per year. And we're going to see how much we have in our bank account after 4 years. And then more specifically, we're going to evaluate how much of that was just interest earned. All right, so let's break down all of our pieces of our equation. 5,000 was our principal or initial amount, so that's our P value. 4% is our R value, but we're going to change that to its decimal equivalent, which is 0.04. 4 years is the amount of time it's going to be calculated, so T is 4. And it's happening annually that we are collecting interest, so N is going to be 1. All right, so let's figure out how much money we have after 4 years after sitting in our bank. So we're going to say 5,000 times 1 plus 0.04 divided by 1. You could just say 0.04 since dividing by 1 doesn't do anything. And then we're going to raise that to the 1 times 4 power, or just 4 if you want to do that instead. It is helpful to be able to use your calculator and do this in one statement. So you will sometimes have to use an extra set of parentheses around that quotient there if we weren't dividing by 1. Maybe we'll see that in another example, excuse me. All right, so doing that on our calculator, we get $5,849 approximately. And so how much of that was just straight interest or our money making money for us? So let's subtract our original investment, subtract that principal amount. So the amount of interest earned was the difference, $849.29. So that's kind of nice. Put $5,000 in the bank and wait 4 years and you make $850. All right, in the next example, we're going to play around with this other version of the formula. This being what happens when our compound interest increases without bound. So our n value is going to be a really big value. What happens when n approaches infinity is that that piece of our equation just turns into e. We did that in a previous lesson. So let's see what happens when we do something similar but use this equation instead. And we're going to compare that to a couple more examples, still practicing that equation as well. So this time we're going to start with $12,000. Our account is going to give us 2.5% interest. We're going to leave it in there for 4 years. And we're going to compare a couple of different ways here. What if it compounds or evaluates quarterly? So our n is going to be 4. Compared to what happens if it were to collect interest monthly. And then we'll compare that finally with just what happens if it grew continuously. So for part A, we're going to say n is 4. And in this case, if you're doing it on your calculator, again, putting an extra set of parentheses around that quotient will help your calculator know what you're doing a little better. We get about $13,258. If we calculate our interest monthly, instead our n value is going to be 12, otherwise everything else is the same. Calculating that, we get about $13,261. And then lastly, if we use this equation instead, plug that into our calculator, we get about $13,262. So we notice that compounding continuously, if all other variables are the same, gives us a better result. However, that's not necessarily always true. Again, that's only if all of the variables are the same. If our annual interest rate or some other interest rate compounded at different times was to increase compared to the same interest rate continuously, well then maybe these values might increase and be actually better. So if all values are the same, compounding continuously will always result in a better amount. But that doesn't mean that it's always going to be the best option. Maybe you could also notice that just putting that amount of money in for only 4 years does give us, about $1,000, $1,200 extra dollars there. But the difference between compounding quarterly and monthly is really not that big a difference. And even compounding continuously is not that much bigger. So that short amount of time for investing is not necessarily the best, although it did give us somewhat a good amount of money. Obviously, the longer you invest, the more interest you would gain and the better your investment. All right, let's move on into science here, chemistry. Let's look at a radioactive substance. And it has a half-life of about 29 years. Simply thinking, a half-life is where the mass is cut in half. So our substance is shrinking or losing substance, I guess. So in 29 years, it will lose half its mass. One way to think about it. We're given the equation to evaluate it, so we just got to plug in values in the right spot here. Whenever you're thinking about initial mass, or in physics, if you're thinking about initial positions, your t-value or time is always going to be 0. What are we starting with before we've started the clock is another way of thinking about it. So if I was to plug 0 in for t into this equation, raising anything to the 0 power is just going to result in 1. And so that coefficient in front is actually going to be your initial value. So we're starting with 10 grams of this substance. In 29 years, we would have 5 grams. In another 29 years, we would have 2.5 grams. So we're a little bit past 2 half-lives here at 80 years. So we should be less than 2.5. Let's evaluate it using our calculator. And we can see that we are, in fact, less than 2.5. We're at about 1.5 grams. One more time. Population growth and statistics. Anytime we're comparing some growth in some population, whether they're flies or bunnies or robots, whatever is growing in population, we can use this continuous growth function. So we're actually given a version of it to try out. If we think about what we just talked about with that initial number, that starting position or starting number, it's always going to be that coefficient because your t-value is 0, making all of this equal to 1, so 20 times 1 is just 20. So we're starting with 20 fruit flies in this experiment, and we're asked to find how many fruit flies we have after 72 hours. So these 20 fruit flies are reproducing exponentially here. T is represented by hours, so we're going to plug 72 into that T spot, use our calculator, and it tells us it's about 173 flies. It's important to note that when you're talking about populations, we don't want to have decimal values. We want to just round down. All right, so there's some examples of using our exponential growth equations or exponential decreasing functions like radioactive decay. And a little bit about investments. Keep practicing using those equations, and we'll keep practicing more examples in class.